All right. A little more complicated. An object pushed at an angle. Uh, Friction is not zero. The mass is m, and the applied force is F. The coefficient of friction is mu, and the normal force is Fn. Find the net work. Well, if there's friction, there is obviously which is doing work. It's not Fy because that's perpendicular to the movement. It's only Fx that's doing the work because it's moving in the direction of the force. It's actually doing positive work, but friction is doing negative work because friction acts this way. If you're acting 180 degrees to the movement's to the left, friction acts to the right. So 180 degrees to the movement, to the displacement, that's negative work. So what is the net work or the total work? Well, W equals, let's always start with the positive works. It's the Fx, which is the applied force is F, cosine of that angle. It's the positive work. Um, okay, minus the friction, which is mu. This is so mu times normal. That's the net force multiplied by the distance that it was, it doesn't mention the distance, we'll call it d. So there's the net work. But we'll have to go back to the first quarter. How do you find the normal force? It does not equal mg, even though that lawnmower is on a horizontal surface, because what we do is we say, to find normal force, we say the sum of the forces in the y direction equals zero. So the up forces equal the down forces. And the down force is F sine theta. And the up force is the normal force. Oops, there's another down force. It's mg. Yeah, mg, the weight of the lawnmower. So these two forces equal the normal. The These are actually down forces. I messed it up. Down force equals the up. So we have to replace normal with this. So I'm going to clean this up because I've run out of room. All right. As usual, I didn't give you enough room, but that's okay. You'll figure it out. You probably write smaller than I do. So the work equals F cosine theta minus mu. And let's see if we remember what normal equals. It equals mg plus F applied times sine theta. That's your normal. And all that's times mu, so that's good. And then multiply it by the distance traveled, because work is the net force times the distance traveled. This is the positive work, and that's the negative work. So let me take a look at what I got here and see if it's correct. Okay, let's take a look, and I think, yep, that is it. Okay, that's the answer. So let's go over this because that was a lot. What is the net work? Well, there are two kinds of work being done in this object. She's doing the positive work, but only her horizontal component is doing any work at all because Fy does no work at all. It's perpendicular to the displacement of the lawnmower. It's the Fx that's doing work, that's doing positive work. The friction's doing negative work. And because of that applied force, that normal force has mg in it, but it also has F sine theta because the up force is equal to down force. And there you go. There it is there. Little tricky. What is the minimum work needed to push a 950 kilogram car 810 meters up an incline? Now, very important. When are you doing minimum work? What's the least work you do in pushing up this car? Well, work is at its minimum when you're moving with constant velocity, which of course means A equals zero, then F net equals zero. That's really important that you know work is at minimum. What's the least work? Think about what's the least. You have to move something up a ramp. What's the least work you could do? Don't accelerate it. Move it at constant velocity. So A equals zero and F net equals zero. So back to first quarter, how would F net be equal to zero when the up force equals the down force? Your applied force is the up force. The down force would be mg. I think there's no friction. That's good. Mg sine theta. Then you would have that force, that applied force, would be the minimum force. And now let's do the work. Work is F applied, which is mg sine theta. That's the force you would apply times distance. And let's plug it in. Let me just double check I got it right. Mg sine theta. Okay, good. Yep, looks good. Now I got a sheet over here working everything out with 9.8. So I think I'm gonna do that, and you can work it out with 10. Let's see. You'll see if we can get a similar answer. So I'm gonna work it out with 9.8, because my key has it. 950 kilograms. That's m times. They use 9.8 meters per second squared. You can use 10. You know that. Sine of 9 degrees. All that multiplied by the d that they gave you, which is 810 meters. So I hope you'll get something similar to what I get using 10. And the answer that my key has is 1.2 in two significant digits, 1.2 times 10 to the sixth. Is that right? Yep, joules. So 1.2 million joules to do this. Oh, I didn't say it. Joule or Newton meters. Why did I get Newton meters? Because, well, F times D is Newton meters. And I never mentioned that's funny. I never mentioned the unit. Very strange over here. I really should have given you the units for work. It's joules, which I think you learned about last year in chemistry. So the units for work is in newtons times meter, or Newton times a meter is a joule. Same thing. So what happens now, B, if the friction is present? Well, now, okay, you still want the minimum work. Work is minimum when A equals 0, constant velocity, and F net equals 0. That's when you're doing the least amount of work. So this is a lot more complicated. When is F net equals 0? When the sum of the forces in the x direction equals 0. When your applied force equals the mg sine theta that's coming down, and what else is coming down? So that's the up the ramp as you push it up the ramp, and what's down the ramp would be mg cosine theta. That's the perpendicular component times mu. So that's just the applied force, and work. The minimum work would be F applied times D. So the work is the minimum, the force, which is that you need to apply mg sine theta plus mg cosine theta mu, that is your force, times d. And I'm going to double check at my key here, see how I did. And let's see, looks good to me. Very good. So now you have to just put the numbers in. So what's the work? Mg. And I think this is all worked out with 9. Pretty sure it's worked out with 9.8. So I'm going to use 9.8. You can use 10. 950 kilograms, we're given that, times 9.8 meters per second squared, times sine of 9 degrees. Oops. 9 degrees. Plus, again, 950 kilograms times 9.8 again, because I think the key I got has that cosine of 9 degrees. It's getting pretty hairy, huh? Cosine 9 degrees. All of that multiplied by the distance that this thing was done, because work is the combination of force and distance, and the distance is 810. And that turns out to be, when you punch it through, let's see, what does it get? We get in two significant digits. We're using 9.8, 3.0 times 10 to the 6 of 3 million. So now you're going to need 3 million. Before, without friction, you need 1.2 million joules. Now you need 3 million joules because of friction. You need to do more work because of that negative work of friction. Okay? So that, well, you know what I left out? This coefficient, left out the 0.25. That goes right over here. That's the coefficient of friction given. That's unitless, 0.25. And so there you go. That's pretty hairy. I think it's a good place to stop.